I'm Peter Norvig, Director of Research at Google. We're very excited today to have with us Jeff Hawkins and Subutai Ahmad. Jeff is the founder and inventor of the Palm Pilot, the founder of the Redwood Center for Theoretical Neuroscience, and Numenta, a company for practical neuroscience. He's the author of On Intelligence, a 2004 book, and a recent book this year called 1,000 Brains, a New Theory of Intelligence. And Subutai is the VP of Research at Numenta and a PhD concentrating in computational neuroscience and machine learning. Jeff, can you tell us about this 1,000 Brains theory?
Yeah, thank you, Peter. And it's a pleasure to be here. So as you point out, I'm here with my colleague, Subutai Ahmad. We're both going to be speaking today. I'm going to speak a little bit first, and he's going to speak a little bit later. Let me just tell you about what we do before what we've learned. And so we run a small research company called Numenta. It's in Redwood City, California. And we have two research agendas. The first is a neuroscience one, as you mentioned. It's to reverse engineer the neocortex, to figure out how it works, what it does, and how it works. It's a very biological neuroscience research agenda. The second research agenda relates to machine learning and AI. And we want to take the principles that we've learned from studying the brain and apply them to improving existing machine learning techniques and ultimately building true intelligent machines. So we've been at this for about 20 years. And over the last 10 years, we've actually made quite significant progress. First on the neuroscience agenda. I'm going to tell you about it today. It's pretty exciting. I think it's exciting, the things we've learned. And about 3 years ago, we've really started applying some of those principles to machine learning and laid a roadmap of AI. And Subutai is going to talk about that work. I'm more the neuroscience person. He's more the machine learning person, but we can both stand in for the other at times. But he's really heading up the AI and machine learning effort. So we're going to do that. I'm going to give a 10, 12 minute talk about what we've learned about brains. And then maybe I'll take a few questions, and then Subutai will talk about what we've done in machine learning, which is also really exciting. And then we can open up for a discussion and questions. Does that sounds like a good thing to do? We'll do that. All right, so I'm just going to jump in. In a very short period of time here, I'm going to tell you what we've learned about how brains work, which is, as I said, pretty exciting. So if you think about the human brain, about 70% of it, or about 3/4 of it, is occupied by the neocortex, and it is the organ of intelligence. So if you look at a picture of a brain, you've all seen the wrinkly thing on top. That's the neocortex. It is a sheet of neural tissue. It's about the size of a large dinner napkin, and it's about 2.5 millimeters thick. It's responsible for pretty much everything we think about as intelligence. Hearing, touch, anything you're aware that you're perceiving is going on in the neocortex. Language, whether it's spoken language or written language, creating it and understanding it, the language of music, mathematics, physics, all that is happening in the neocortex. And pretty much every high-level cognitive function we think about as part of the human condition, whether it's engineering, physics, math, politics, whatever, that's all happening in the neocortex. So understanding what it does and how it doesn't is a pretty important component to moving towards basically understanding who we are and perhaps building intelligent machines. And so let's just delve into it a bit. One of the most remarkable things about the neocortex is that if you cut into it, you slice it and look at the 2.5 millimeter thickness, you'll see this incredibly complex circuitry. There are many different types of neurons that are connected in very specific and complex ways and range in these different layers. It is not like the kind of neural networks we study today in machine learning, which are much more uniform. This is a very complex circuit that's in there. And what's really remarkable about it is if you cut into the part, you see the circuit, but if you cut into any part of the neocortex, you see the same basic circuit. There's some small variations, but it's remarkably preserved. In fact, if you cut into a rat's brain or a dog or a monkey's brain, and you cut through the neocortex, you'll see the same circuitry. It's a kind of amazing discovery. And it was the first person who made sense of this is a guy named Vernon Mountcastle, a famous neurophysiologist, who said, the reason that the circuitry looks the same everywhere is that it's all doing the same thing. That is, there's the same intrinsic functionality to the neocortex for everything it does. And so he said, if you took a section of the neocortex and you hooked up to your eyes, you get vision. If you hook up to your ears, you get hearing. If you hook up to your skin, you get touch. And if you take the output of some of these regions of the cortex and feed them into other regions, you get high-level thought and language. This is hard to believe, but there's a tremendous amount of empirical evidence supporting it, and it's basically a fact now. This led to the idea of what you might have heard called a common cortical algorithm, meaning that there's this common thing that's going on in the cortex everywhere. And so our research is very much along the lines of answering three questions. What do the cortical columns do? How do they do it? And how do they work together to create our perception of the world and our intelligence? And as I said, we've made really great progress on answering those three questions. So let me just delve into it. I'm going to lay it on you really quickly here. I'll keep it very high level. And so it shouldn't be too hard to follow. It isn't that hard to understand in conceptual levels. What you think about is that each of these cortical columns, now I didn't tell you how big they are. I should do that. They're about, they span the entire 2.5 millimeter thickness of the cortex, and they're about roughly 1 millimeter in area. So you can think of them like little grains of rice. So your cortex is composed of these little grains of rice stacked next to each other. And there's about 150,000 of them. So that's what we're talking about, this little grain of rice type of size thing, of which you have 150,000 of them in your head. There's about 100,000 neurons in each one of those little columns, so it's complex. All right, so what does this cortical column do? Well, the simplest way to think about it is that each one is like a little miniature brain. Each one builds models of the world. Each one gets input. Each one processes input. Each one builds a model of its sensory input. Each one actually generates behavior. Every column in your cortex actually generates behavior. And we say that they're sensory motor models. And why do we call them sensory motor models? Think about, there's a column that gets input from the tip of your finger. So there's columns that get input from the tip of my finger here. And when I touch something like this coffee cup, there's a sensation what I'm feeling, like an edge, a little rounded edge. And that gets sent to the brain. But it's sensory motor because the columns actually know how my finger moves. So as I move my finger over this cup, the column is being told how the finger is moving. And therefore, it's able to integrate both the sensation and the location of the finger over time to build a model, in some sense, a three-dimensional structure of the cup as you move your finger over it. Like, oh, it's curved on this area, and it's down here. There's another area that's rougher, and there's a handle over here, that kind of thing. So you might think that a column just getting the input from the tip of the finger isn't really very smart, but by integrating information over time and movement information over time, it's able to build models of the world. And model building is the essence of intelligence. It's how we understand the world and how we act upon the world. We build models. So the surprising thing about this is that every column in the cortex is building models. That's not how we think about neural networks. Most people don't think about neural networks. Most people hadn't thought about the cortex that way. And so we can then ask ourselves, well, how does it do this? What are the methods it does this with? And we describe it as internal to these individual grains of rice, these that are getting these inputs from like your finger. Maybe I should step back a second and say, like, even vision works this way. You may not think of it that way, but vision works this way too. When you look at something, the columns in your cortex each only see an input from a small part of your retina. It's like they're looking at the world through a straw, a very narrow straw. And so each column then integrates, as your eyes constantly move around the world, integrates what they're seeing as the eyes are moving, and it builds up these models. All right, so how does it do this? Internal to these each column, what we call reference frames. You can think of a reference frame like the Cartesian coordinates you learned in high school, X, Y, and Z. It's a way of structuring information. So literally, when you touch or see something or hear something, your brain is building this sort of three-dimensional model of the things as the sensory movements are occurring over time, and is assigning knowledge in a reference frame. It's just saying, okay, here's a structure for this thing, and I'm going to assign what I'm sensing to different points or locations in that structure. It's kind of like that. It's a little different, but it's kind of like that. And so it builds up this model of things as you touch it or as you move your eyes around and rotate things in your head, things like that. And so now we have these 150,000 columns, all learning models. Some are learning models from the input from the eyes, some from the ears, some from the skin, some from other parts of the brain. So then we ask yourself, well, where is knowledge of something stored in your head? If I ask myself, where is knowledge of this coffee cup stored in your head? Well, it's not stored in one place. There isn't a single model of this coffee cup in your head. There are thousands of models. There are hundreds of thousands of models in your visual areas of your cortex. There's hundreds of thousands of models in your somatosensory areas of your cortex. You even have models of how coffee cups sound as you use them, and what sounds they make when they're filled with liquid and not filled with liquid, things like that. And so we call this the thousand brains theory. It's not that every column in your cortex learns models of everything. That's not true. There's 150,000 columns, and maybe a few thousand have learned columns of coffee cups. But it's 1,000 brains because these sort of independent modeling units are occurring at the same time. Which leads us to the next big question. How do they work together? Why do we not feel like 150,000 little brains, you know? And this occurs because the columns, they talk to each other. There's these long-range connections that go across the entire neocortex where the columns communicate with each other. And essentially what they do is they vote. If imagine I have this coffee cup and I'm now touching it with multiple fingers at the same time. And if I grab this coffee cup, I may not have to move my fingers to recognize what it is. I reach my hand in a box and I grab this thing. Oh, I know it's a coffee cup. What's going on there? Column that's getting part of input from this cup doesn't know what it is. Each column is saying, I'm feeling an edge, I'm feeling a curve, I'm feeling a flat surface, and here's where it is, here's where it might be. And they vote together doing these long-range connections, and they reach a consensus. And they said, okay, the only thing consistent with what we're all sensing right now is this coffee cup. So that is what we're going to say the answer is. It's a coffee cup. And so these long-range connections across the brain form these representations of what the objects you are. And that's really all you're worried about, or you're aware about. Vision is the same thing. When you look at something like this, you can say, oh, I can flash this image of a dog or a cat in front of your face and say, what is it? You can answer it. And the reason is because individual columns all have different models of the things they're trying to understand, and all get a different part of that input, and they vote to say, what is consistent here? What is the only thing that's consistent? So you have these thousands of models that are voting to reach consistent hypotheses about the world. And they do this with these long-range connections. And you are only perceptually aware of the voting. You're not aware of what's going on underneath. So normally when you're looking at something, your eyes are moving about 3 times a second, and you're not aware that the input your brain is changing constantly. The columns are all processing information, changing over time as you do that. But the voting neurons are reaching the same consensus. I'm listening to this guy, Jeff Hawkins, talking, even though my eyes are moving over his head, and I don't really see that. So that's, you perceive the voting neurons. So that's the basics of this theory. What we discovered is that the cortex is this huge modeling system. It's built up of many, many, many thousands of models. Each one of those models is working on the same basic principle. They're not really doing different things. There's not a different algorithm for vision and hearing and touch or anything like that. They're all using the same algorithm, and that they vote to reach a consensus. There is two other things I want to mention about how the details of these things work. Because when we talk about the relevance of this work for AI, like, do we care how the brain does this? You know, is it important how the brain thinks and how it learns about the world? You might argue that's maybe not that important, but I would argue it's very important. We have an example here of how it does this, and there's principles we can learn, and those principles we can decide whether or not we need them or not need them, or how we'd implement them differently than a brain. So there's 2 more principles I want to talk about, and they're a little bit more detailed. One has to do with the way neurons work. So a neuron is the cells in the brain. We have about 18 billion neurons in your neocortex. And as we typically model them in machine learning, they're very simple structures. They're called a point neuron. It's like a little circle and a whole bunch of inputs come into it. But real neurons are not like that at all. Real neurons have this complex structure called dendrites, which is like a tree. You've probably seen pictures of these where there's these branches of a tree coming out of each cell. And most of the synapses are arranged along those branches on the dendrites. Well, we now understand what's going on in those dendrites and why they're there and how they process information. In fact, most of the processing that goes on in your brain actually occurs inside the dendrites of a neuron, not between neurons. And most of the synapses are on these connections are on the dendrites. And the simplest way to understand this is that these dendrites allow the neurons to represent something in different contexts. I won't explain how it does that here. But imagine I have some input. I want to represent that input in different contexts. I'm seeing a dog. It's my dog in my living room that doing something I'm expecting it to do at this time of day. The brain constantly has to provide context for everything it's doing. And these dendrites do that. They're a very important component of how it works. And the last thing I want to talk about, one more essential property, I'm going even deeper now into neuroscience, is something called sparsity. if you were to look at the neurons in your brain, and let's say we just look at 10,000 of them, or just sitting there representing something, take a group of 10,000 neurons, you would see, typically, you would only see 1 or 2 or 3% of the cells active at any point in time. That most would be quiet, silent, not doing anything, and maybe 2%, or say 200, are active. And a moment later, a different 200, and later, a different 200 are active. And a moment later, a different 200 are active. This is the way the brain works. If all the neurons in your brain become active at once, it's called a seizure. So we don't want that. This is different than how we typically do artificial neural networks, where all the neurons are somewhat active at any point in time. But in the brain, it's not like that. And there's another type of sparsity, which is called connectivity sparsity. If I have 2 groups of neurons and they're connected to each other, we typically do that in machine learning by connecting all the neurons to all the other neurons. But in the brain, you don't see that. You see a very sparse connectivity. Now, I mention all this because these are actually the properties we think are absolutely essential for creating intelligent machines and for creating an AI, artificial general intelligence. I'll give you just a brief hint at why these properties might be important. Take the activation sparsity. Often in the brain, we are not certain of the answer to something. We're not sure what we're looking at. We're not sure what's happening. We're trying to guess what's going on. So we have some kind of uncertainty. A mathematician would represent uncertainty using perhaps a probability function. They'd say, oh, well, there's a probability it's this, and X probability it's that, and so on. And they add up to 1. That's what probabilities do. The brain doesn't work like that at all. It turns out when you use sparsity, sparse activations, the brain can represent multiple hypotheses at the same time. So let's say I'm using 200 neurons active to represent something out of 10,000. So I have 200 active out of 10,000. It turns out you can activate 5 or 10 of patterns. And so you might have a couple of thousand neurons active at the same time. And you think that would make a big muddled mess, but it turns out it doesn't. It turns out because the brain works on sparsity, that all 10 hypotheses can be processed at the same time. It's a different way of handling uncertainty. The brain is constantly processing multiple simultaneous hypotheses at the same time, and nobody gets confused, and it's only because they use sparse representations. So this is like a fundamental information processing idea, like you might, like binary digits or in computers. So we think these things are essential. So I'm done. We've made a lot of progress understanding how the neocortex works. We haven't figured it all out, but we have the big picture. We have a lot of the details. There's more details we figured out. But it's allowed us to sort of lay out a roadmap, like, okay, I have a good sense of what intelligence is. I know how the brain does this. And we can start building this stuff into machine learning. I should point out that everything I'm talking about here has been published in scientific papers, and it's also discussed in the book that I wrote recently, 1,000 Brains. But this was like the shortest introduction I think I could give to you. So I'm done with my part there.
Thanks, Jeff. That was great. I did have a question about how the neocortex works. So you mentioned your dog in your living room, and presumably that dog's got the same kind of neocortex and the same kind of little grains of rice, but they're never going to speak English. So something different is going on. And then on the other hand, we see all these things of crows and ravens doing really smart stuff, but they've got a pallium and not a neocortex. And BPR in the comments says even jumping spiders have plans and memories and so on. So what's going on there?
Yeah, so let's talk about the second part of your question first. It turns out birds don't have a proper neocortex. But they do have these things called blobs. That's the technical term sometimes they use. And it's become clear recently, there's a lot of evidence that actually the same neural mechanisms are going on in those blobs as are going on in the cortex. It's possible that nature has discovered multiple ways of building models of the world. I'm sure it has. But the way that's going on in mammals is a really powerful way, and it would have evolved a long time ago because it basically allows us to move around in the world. And so I would suspect any animal like a bird is going to have the same basic mechanisms, even though there may not be, quote, equivalent to cortical columns, and they may not be an equivalent cortex. In fact, the mechanisms that we think are going on in the neocortex, the very specific mechanisms, were first discovered in an older part of the human brain called the Anthorino Cortex and the hippocampus. And there aren't proper cortical columns there, but these cell types and their circuitries exist in a different form. It's like what nature did is just discover these neural processes that allow us to build models of the world, and then it's repackaged them in different ways. And then when it came to the mammal neocortex, it found a very efficient packing scheme and said, oh, I can make a lot of those now really quickly just by replicating this. I don't know about, jumping spiders. They may have a totally different way of doing it. And I wouldn't say the jumping spider isn't smart or not. I say intelligence has to do with learning a model of the world and using that model to act upon the world. It's not about being able to solve particular tasks. A jumping spider may have genetic algorithms that tell it exactly how to do what it does. I don't know enough about jumping spiders. I don't know anything about jumping spiders. So, but if an animal can learn models of the world, there may be other ways of doing it, but this is the way that mammals do it. And I think it's the same way that birds do it. And it could be another. It's probably an evolutionary, very old mechanism, even though it's been packaged differently in the human. Now, the first part of your question had to do with dogs and language, really. It had to do with language. And I did address this in the book a bit because language is an odd thing. First of all, language only appears on one side of your brain, the left side, which is unique. It's almost the only thing that sounds like that. And so why is it unique? Does it work on different principles? Well, if you look at the neural tissue in the regions of the cortex that do language, they look a lot like the neural tissue elsewhere. I've heard two good hypotheses why humans have language and other animals don't. I don't know if either one is right, but I'm happy to share them with you. So one has to do with language requires a very fast processing, much faster than most of the things we do. And if you look at the language areas of the brain, they have extra insulation called myelination, which allows them to operate faster. And that's the hypothesis why it occurs on one of the hypotheses why it occurs on one side of the brain, not the other. And that insulation is expensive, biologically expensive, so you don't want to do it everywhere. And so that's one hypothesis. Another hypothesis is, which I also think is interesting, is the cortex, to create language, you have to be able to control, the cortex has to be able to control certain parts of your musculature. The lungs, the voice box, the mouth, and the tongue have to be all very tightly controlled by the cortex. And there's some evidence that the pathways that come from the cortex to the rest of the body in other animals do not project in the same ways, that other animals are not able to move their voice box because the cortex is physically not connected to it. And in mammal, at least in humans, that pathway is developed very strongly, I should say, in humans. So I don't know the answer to this question, but the evidence we have so far does not suggest language is fundamentally different. It's going to be different in quantity or different in certain attributes. There may even be an extra cell type or something. But if you look at the anatomy of the cortex that controls language, it's almost identical to anatomy elsewhere. You can also make an argument about the structure of language is similar to the type of structure we see in objects in the world. It's this hierarchical recursive structure, and these neural circuits can do all that. So.
Okay.
That's the best I can do on that one.
Yeah, thank you. And Subutai, you're going to tell us how machine learning fits into all this.
Yeah, thank you, Peter. So I'll plan on taking about 5 or 10 minutes as well to kind of describe kind of the details of our research roadmap. Our approaches at Numenta is quite unusual and really exciting. So I'll make sort of one high-level comment first. Our process here is to look at kind of different elements of the thousand brains theory that Jeff described and the set of the fundamental capabilities that we know have to be present in general intelligent systems. And then for each of those capabilities, we try to understand what can we learn from the neuroscience at a very basic mechanistic level that we can actually implement as algorithms. And we're not trying to match a specific neuroscience experiment or try to explain some sort of high-level property or manifold or anything like that. We're trying to extract sort of fundamental algorithmic lessons that can be incorporated into a coherent system, taking neuroscience as setting a set of constraints and mechanisms. So it's very much a computer science approach. Now, there's a ton of fantastic research going on in deep learning today. And as a small research lab at Numenta, we try to focus on a specific set of capabilities that we think can solve big problems with state-of-the-art deep learning systems today and where we can learn from the neuroscience. So let's get into it. So using the thousand brains theory as a framework and taking sort of all this stuff into account, I'm going to describe 3 aspects of our roadmap, and I'll kind of go in the reverse order that Jeff went. So I'll talk the first about sparsity. So that's a fundamental aspect of our research roadmap. So Jeff discussed that the brain is really sparse. Very few neurons are actually active at any point in time. It's somewhere around 2% or less of your neurons in the neocortex are active. And even when 2 sets of neurons project to one another, the connectivity between them is also extremely sparse. is somewhere around 5% of the neurons are around actually connected. So most of the neurons are not active and most of them are not connected. This is extremely sparse, much, much sparser than what we have in typical deep learning systems. And the question is this just happenstance, or is there an important benefit to sparsity? And it turns out there are actually several benefits. Jeff mentioned one about being able to represent multiple hypotheses simultaneously. I'm going to talk about two that we really looked at in the context of machine learning systems. The first pretty obvious one is efficiency. When things are sparse, when they're silent, they're not consuming power. And we all know today that deep learning systems consume a huge amount of energy and are incredibly inefficient compared to the brain. The neocortex actually only uses about 40 watts of power, which is incredible. It's like a little light bulb. And by incorporating sparsity into deep learning systems in the way that it seems to be implemented in the neocortex, we've actually been able to recently show that it's possible to improve the efficiency of deep learning systems by several orders of magnitude. So if you look at convolutional layers and linear layers, we can actually improve efficiency by over 100 times, so 2 orders of magnitude. We did this on FPGAs, where we can directly control the circuitry and look at things at a very detailed level. More recently, we've actually now started to see that we can replicate this on CPUs, and then potentially even on TPUs and GPUs. Now, for those latter systems, they might need some new circuitry, and they'll need to evolve towards supporting sparsity more inherently. But we think there's a tremendous amount of promise to this, and we're starting to understand at a very detailed circuit level what's required to sort of fulfill kind of the efficiency promise of sparsity. Very recently, we've started scaling some of these to ImageNet size data sets and transformer architecture. So we're pretty confident that the core principles will actually apply to even sort of the large scale networks that we're using in machine learning today. Another property of sparsity is that sparse vectors, so these are very high dimensional mathematical vectors that are mostly zero, actually minimally interfere with one another. When you have sparse representations, they don't collide much with one another. And because of that, it actually looks like sparse systems can be far more robust to noise and very robust to perturbations compared to typical dense systems. We can sort of characterize this mathematically, and we've shown in some experiments a couple of years ago that if you just add random noise or perturbations, these sparse systems can be a lot more stable. So we think robustness, when we think about building systems that are not brittle, we think sparsity should be one of the core components of that. So kind of summarizing the first aspect of our roadmap, we think sparsity is going to be critical for scaling AI systems. Is really the only way we're going to scale to really brain scale and much larger systems, and also going to be critical for robustness. A second aspect of our research roadmap has to do with perhaps the most fundamental thing in neuroscience and deep learning, which is the neuron itself. And Jeff described a little bit about the dendritic branches and how they incorporate context and so on. And I think this is one of the most underappreciated aspects of neuroscience, just how complicated an individual neuron actually is. And the neurons we use today in deep learning systems are simple point neurons. They just take a linear weighted sum of their inputs and a nonlinearity. But real biological neurons are nothing like that. And I think in machine learning, researchers sort of know this, but the prevailing viewpoint is that, okay, if we just add more and more parameters and just make the system bigger, we can sort of make up for the increased complexity of neurons. And that's not true. There are important functional properties of real neurons that we should consider. Real neurons have complex temporal dynamics. They actually have a diversity of different learning rules depending on where in the dendrites you are and depending on the situation. They have sophisticated heterogeneous morphology and structure. And we think these properties are actually going to be important to incorporate in intelligent systems. Very recently, we've been looking at how we can do that. We think some of these properties are going to make neurons and networks amenable to continuous learning. So the ability to continually learn new things without forgetting what's happened in the past. We have shown in some of our papers that biological neurons are actually constantly making predictions, and they're learning from mistakes in their predictions. This is a very different learning paradigm from the typical kind of supervised learning paradigm that we used with backpropagation today. And all these learning rules are actually completely embedded within the neuron. There's no external homunculus or system that's computing some sort of a global loss function and there's no sort of rigid backpropagation phase that's going on globally throughout the network. So understanding these kind of details will lead to the ability to develop these continually learning, completely self-supervised systems. They will have completely local learning rules and therefore can scale really, really well in hardware. And very recently, we've shown that by augmenting the neurons we use in deep learning, we can make them sort of closer to biological neurons by incorporating context and sparsity and updating the learning rules. We can mitigate to a large extent some of these issues around catastrophic forgetting that you see in sort of classic deep learning systems. We're hopeful that we can get to a purely local unsupervised learning system as well that's as good as systems that are trained via end-to-end backpropagation. So this is all research in progress. We definitely have ways to go, but incorporating these essential properties of real neurons is a second really important part of our research. The third thing I wanted to highlight is reference frames. So Jeff described this earlier. It's an area that actually Jeff Hinton has been thinking about for over 40 years. There's a paper by him back in 1981 that discusses it. And I think it's actually really fun to go back and read those old papers. But as Jeff Hawkins mentioned, with the discovery of grid cells and place cells in neuroscience, we understand a lot more about how reference frames are implemented in the brain and how critically integrated it is with movement and behavior. So from a deep learning standpoint, again, going back to the machine learning and practical side, incorporating this is going to be critical. Reference frames essentially allow us to create a single invariant structure or a stable structure that completely describes an object or a concept in a manner that you can actually navigate and manipulate. So a simple example is, imagine I show you a strange new car that you've never seen before. With a single image, you can instantly create a representation of it based around reference frames. And you can imagine immediately what it would look like from the other side. You can imagine how it would feel and how it would sound. You can tell immediately, okay, is it going to fit in my garage? It's going to fit in your garage because you have a reference frame for your garage too, and you can relate these two reference frames. You could probably imagine different ways you can move the car into your garage as well. So all of these things are sort of inherently come from this structure. And by incorporating reference frames and these properties into machine learning and creating these invariant structures, we think we'll be able to dramatically increase the generalization power of our systems and dramatically lower the number of training examples that we'll need. These systems will be able to plan and naturally integrate behavior because moving around reference frames is an essential part of how they're created and how we learn about structure in the world. It's going to be critical for robotics. And since these systems will also have the other properties I mentioned, they will also be power efficient, continually learning, and so on. So we still have a ways to go on this side as well, but this is a very sort of interesting and active area of our research roadmap. So I've sort of covered three different aspects here. I discussed sparsity and how we can use that to get dramatic efficiency gains on hardware and improve robustness. I talked about the importance of the neuron model itself and how that can lead to continually learning systems that can learn in a local, self-supervised manner. I talked about reference frames and grid cells and how we can get dramatically better generalization, integrated sensory motor processing, and smaller kind of training sets. If you kind of step back, one big theme maybe I want everyone to kind of take away from this roadmap is that each of these are not just point solutions. We're not trying to solve each of these problems independently of the other. Instead, what's really exciting to me is that from neuroscience, it actually tells us that these are all components of a big integrated framework. So when you think of a real-time autonomous intelligence system embodied in some environment, all of these properties are going to come into play. And ultimately, you can ask, do we need to use brains to get to intelligent systems? Ultimately, I think that's where the hope is. The brain provides a concrete existence proof that these algorithmic components can be put together into a single working intelligence system that's consistent. The whole theory of cortical columns shows that there is a common microcircuitry and common architecture that if we implement and through this model voting process, we can scale this. That single system is going to be able to learn a diverse range of tasks. It's going to be able to learn these continuously in a very, very power efficient way. So when we look at the neuroscience, these are the sorts of things that really drives me, and that's what we're trying to work on at Dementa. So hopefully that gives you a brief sense of. I went very quickly, and I'm happy to take more questions on the details, but that gives you a sense of kind of how we approach things and how we're taking neuroscience into a research roadmap.
That's great. And, of course, there's so much going on now in deep learning research. And I'm thinking you remind me of a lot of things that seem like they align and maybe some things that don't, right? So, at Google, we have this MUM model, which is multimodal, multitask, multi-language, bringing in video and robotics and so on. So it seems like that's aligned with your direction. We've got these switch transformers that do voting and have large portions of the networks turned off for conserving energy. OpenAI had a sparse toolkit. We have a similar kind of sparse toolkit called Regal. LeCun's been doing these dense to sparse pruning, and you mentioned some of the Hinton work. When you look at all this, what do you see that's aligned with your direction, and what do you see where maybe they're missing out from the direction you're going?
Yeah, I think this, we look at a lot of that stuff. I think that stuff's really exciting, and we can learn from those as well. I think many of those concepts are very much aligned with some of the stuff that we learned from the brain as well. I think what we get again from the brain is a lot of detailed mechanisms and a very consistent sort of integrated structure. These are, again, not individual sort of point solutions. They all have to somehow work together. And there's not going to be too many ways of doing it. And so the brain gives us an existence proof that here's something that we know is working. And the field of neuroscience today is exploding. There's so much information and data coming out of it that it gives us a set of constraints and a view into a really detailed structure that we know works, that we could try to reverse engineer. And hopefully we can take the best of what's done in deep learning, take all of the stuff we know from neuroscience, and all of those will be sort of important in creating intelligent systems, I think.
Yeah, I'll add on to that too, a little bit. The way I view it is people who work in machine learning and AI, we all want to achieve somehow the same result in the end. And I don't think there's going to be multiple ways of doing it, just like there aren't really multiple types of Turing machines. You know what I'm saying? That's, there's variations on a theme, but there's going to be some common principles that we use in AI in the future. We're all trying to get there. The question is do you need to study the brain to do that or not? Can you just get there by just positing and doing other ways? Now, I don't think anyone can answer that question. We've always felt like the quickest way to get there is by studying the brain. But I think all these ideas are going to coalesce at some point. That's my point, Peter. I don't think we're going to end up in the future. There are 5 different ways of building intelligent machines. I don't think that's right. I think it's going to be more like computers, where we have the one set of fundamental ideas that can be implemented in different fashions and different variations on a theme. So to me, it's less of a competitive world. It's more like we're all trying to get to the same place. We can all bring different things to the party. I think by studying the brains, we've got a really deep understanding of many of these principles that even take like Jeff Hinton's capsules. It's similar, but we can see that he's missing this motor component out of it and other things. And so we know that has to be added.
And going back even farther, I was a grad student in the 1980s, and we had Minsky's Society of Minds model. Is that related to the 1,000 brains? Or
I was at grad school in the 80s as well, late 80s when backpropagation was just coming out. I think the Society of Minds I think it's actually quite very, very different from the 1,000 brains theory. The Society of Minds, you had, tons of really small, very special purpose bots that would sort of work together, if you will. What we learned from neuroscience is that it's not like that at all. There's a single sort of consistent microcircuit, like cortical column, that's not simple. It's somewhat complex, but then it's repeated 150,000 times, and it's extremely general purpose. It can learn anything that we as humans learn. It's not designed to do any one specific thing, and it's a learning system. It's continually learning. It operates on reference frames, all the stuff that we talked about. So when you look at a very, very high level, it might seem similar, but when you look at the details, actually diametrically opposite, I think. I don't know, Jeff, if you wanted to add more.
I agree. Yeah. I mean, I was excited when that book came out, and then I was disappointed because it was like, well, there's a lot of ideas, but no mechanisms and no biology and no, I was like, and it was all these different things. And it's like, okay, you could have picked this 100 things, maybe you could pick another, 100 things. But at Subutai, what's really amazing about the brain is we have this common algorithm that does everything. and now we understand why it's so powerful. It's just a general purpose modeling system, assuming that you have something that has sensation and movement. And after that, you can learn anything. Well, anything that's learnable, I guess. We don't know what we can learn.
Okay. Let's see. Well, let me take a chance to do, while I've got Jeff here, there's one question I always wanted to ask, and then we'll go to the audience questions. So Jeff, when the Palm Pilot came out in 1997, the first successful digital assistants, and some people then worried, maybe the screen's too small and the tiny little keys are too small. And other people said, oh, well, the portability, that's really awesome. Now, if you told me then that 20 years later, an assistant would have no screen, no keyboard, no portability because it's just a speaker that has to be plugged into the wall, I would have said you're crazy. And yet that device sells pretty well from several manufacturers. So how did personal assistants get here, and where are they going? And when are we really going to be able to?
Yeah, here's the thing about this, Peter. Some people know this story. My first love was neuroscience, and I was a graduate student at Berkeley in the late 80s. And I found out, rather surprisingly, that it wasn't possible to be a theoretical neuroscientist back then. That wasn't a career path. You could not do it. We can go into why. And so I ended up going into computer science as a temporary job. I said, I'll go work on computers for 4 years, and then I'll come back into neuroscience. And that's when we started Palm. And that whole thing just, and of course, when I got started, I realized, oh my God, everyone in the world is going to, I knew this. I knew billions of people are going to own computers in their pockets. And I said, oh my gosh, this is going to sweep the computing industry. It was very clear by 1989, 1990. And so I got really into that. Right. And then we had a lot of success. But at some point along the path, I said, I want to go back to brains. Yeah. And so I left. I just got up and left. Everyone knew it. Everyone knew that's not what I wanted to do. And as important as it was, I felt that studying brains was more important for the future of humanity. And so now your question to me is, the shorter answer to your question is, I don't think about that stuff at all. I don't think about mobile computing. I don't think about digital assistants. I don't think about whatever, okay, Google or hello Siri or Alexa. I just don't. In fact, I'm kind of a Luddite in some ways. It's like, I don't have the audio digital assistant, and I try to, I'm not a gadgeted guy.
Okay.
I can attest to that. As someone who discovered the personal calendar, he's actually really bad at calendaring.
Someday we'll be talking to one of your intelligent digital brains. But we'll give you another decade to get that.
Yeah, I just try to. I'm just focused on brains and AI.
Right. All right, let's go to some of the audience questions.
Let's see, I'm looking at them here too.
Okay, so we got one from Mark Weiss. Any major new insights after the book was published?
Well, full disclosure, Mark is someone we know very well. He's actually an investor in the Meta. So let's just be honest. Hi, Mark. Discoveries that we've made since, what was the question again? I'm sorry.
Since the book was published.
Since the book came out in March, and not a lot. Yeah. What has happened is that some of the predictions in the Thousand Brains theory, one of the sort of major predictions, which I don't think anyone would have anticipated, is that throughout the neocortex, in every cortical column, you'd see grid cells equivalent. These cells that we know about exist in other parts of the brain. So part of our theory is like, hey, those mechanisms in the old part of the brain are replicated in the cortex. And we're starting to see papers come out where they're finding this in primary visual and primary sensory cortex. So this is like sort of the key underpinning. That's not a discovery. That's an empirical evidence supporting it. In terms of discovery, I think there's one idea that on the neuroscience side that I'm working on, which is pretty cool. I haven't published it yet, so it's not anywhere. But this is it's a little bit more detailed. It's like, how does the brain know how everything is moving? How does the brain know where your finger is and how it's moving through the world? And how does it translate that from an egocentric to a body-centric to an object-centric reference frame? And I think I've made some pretty big discoveries on that. So I'm writing up a paper about that now. And I think on Subutai, you might answer that question too, because every week it seems like we're making progress on the AI machine learning stuff. It's like I can't keep up with it. I don't know if there's anything you want to say about that or not.
Yeah, I mean, we're constantly surprised, as we start to incorporate stuff into deep learning, how compatible some of these things can be, and initially it's not obvious that you can take some of these properties and implement it in a deep learning system, but we're able to do that and progress it. Ultimately, I think we're going to end up with something that looks very different from today's deep learning system, but you can actually make incremental progress implementing the neuroscience approach, and that's kind of an interesting.
Yeah, I'll throw out one.
Sort of expected that at first.
Yeah, I'll throw out one teaser because it's a teaser because I'm not going to tell you how we did this. But we've recently figured out how to get a lot of this stuff to work on CPUs, which most people don't think CPUs would be very good at this stuff. So leave that as a teaser.
I do know there's a couple companies that are looking at using CPUs for different. So
well, there's a huge neuromorphic computing industry, right? That people are. It's a field. I don't know if it's an industry yet, where people are doing some radical new designs. Like Rain Neuromorphic, I think is the name, and then people trying to figure out how to enhance CPUs and GPUs. Everybody's racing to do this. Everyone was caught with their pants down a little bit. NVIDIA, sort of took over the AI computing world, and all the other players are trying to figure out how to catch up and leapfrog them.
Yeah. Okay, let's go to another question. You mentioned the cortical columns perform independent frame of reference transformation operations. Have you performed experiments to confirm this?
We don't do experiments. We're like a theoretical group. So, there's theoretical physicists and there's experimental. We work with experimental labs. We have lots of collaborations. We have visiting scientists. So as I mentioned, a theorist can't tell experimentalists what to do. They don't want to hear that. But we do find people are testing our theories one way or the other. I did mention there's some new research that just came out at the beginning of this year in January. The people and they're citing our work. But I imagine those experiments they were started earlier. Maybe not. I actually don't know. But where people are, in some sense, even if they're not explicitly trying to test our theories, they are. And they're aware of our theories, and so when they get these results, they come back and say, yes, this is compatible. This is what you predicted. So that's happening at its own pace. But we don't do any kind of empirical experimental work in our
What's the coolest experimental result you've seen?
What do you think, Subutai?
There's the border ownership cells potentially where you find those are pretty interesting where you typically think of neurons as representing, let's say, some feature at a point in your retina, let's say. But it turns out that even very early on in your visual system, neurons actually respond to features that are relative to the location on the object itself. And that's even in primary visual cortex in V1, that the very earliest stages of processes, sort of equivalent to kind of the first convolutional layer in a network, you actually still see some hint of allocentric.
This gets back to the thing we were talking earlier about context, right? So these cells are like, if it's detecting like a vertical line, or edge, or something like that, it'll say, well, if it's the hind leg of a dog, it's going to fire, but if it's the foreleg of the dog, it's not going to fire. I mean, it's that kind of
even though it's the same angle,
it's the same input to the same input to that column. So that just tells you that column is smart. One argument could be saying, oh, somebody else is telling it from elsewhere in the cortex. But our theory says, no, that column knows what this thing is.
Yeah, and they've actually ruled out the possibility of feedback from above because it happens so quickly. There just isn't time for information to propagate. It has to be computed locally within that column.
Yeah. So the thing that I don't want to put too much effort into this because, experimental results have to be vetted. They have to be reproduced. And so when someone comes out with a new result, you have to be patient. You have to wait a while to see if it's reproducible. But as I did mention, I was really thrilled to see people finding evidence of grid cells in primary visual and primary somatosensory cortex, which is a key prediction of our theory. It doesn't add new insights to it. It's just like, it's nice to have these sort of supporting evidence coming out.
All right, another question. Are there applications to healthcare and life science?
Well, yeah, but we're working at a different level, right? We're working at sort of fundamental algorithmic processing levels. One of the things that's interesting that's come out since the book came out in March is we've had people reach out to us from different fields and who say, hey, this is helpful in my field, whether that's pedagogy, like I study the science of teaching. Well, this is really helpful. Or someone who does, psychiatric diseases. This is really helpful. And so people are trying to apply the general theory to thinking about their individual fields. So that's kind of related to that question. It's not something we do, but it's nice to see people are doing that. But we're not anywhere close right now to. We're not doing practical applications. We're just saying we can speed up these networks by 100 factor of 100. We can make them more robust. We can do all these things. Sort of basic algorithmic level work.
Okay. Another question.
Biological neurons need to satisfy a lot of biological constraints. How do you distinguish which properties of biological neural networks are key for general intelligence, which properties are not? So I repeat that loudly, or can everyone read that? The answer, well, this is a general question about theory, any kind of theory in any field, right? When you're in a scientific field, doesn't matter what it is, if all this experimental evidence, all this empirical evidence is piling up that people don't understand, at least in many fields, they don't understand it. And then you come up with, then you have to come up with a theory about how the system works or how do you explain that. And you have to select, you have to pick what things you're going to focus on and what things you're not going to focus on. This question is like, well, how do we know what properties of neurons that are important, which ones aren't in our theories? Well, the answer is it's hard. It's really, really hard. We don't decide up front. We don't say, oh, we just think these things are important, these things are not important. We use a combination of stuff. Well, and so the evidence, for example, about dendrites is that, well, there's a lot of evidence of doing neural processing. About 20 years ago, they discovered these things called dendritic spikes. And so we now have all this empirical evidence about them and what they do. So they're begging to be cried out, explained. But the general answer is we go as deep as the theory requires. So we have our theories touch on some things, some certain types of neurotransmitters, but we don't get down to the dynamics of gates and ionic channels and things like that. We have a need to do that. If the theory all of a sudden says, well, we have to get down that level, we'll go there. But the way I look at it, our theories cannot contradict any biological facts. That's the way I look at it. If there's a biologically determined fact and our theories contradict it, then we're going to modify our theories. It doesn't mean our theories have to explain every biological fact because we can't do that. It's just too many things. But we'll keep adding biological details as necessary. And that's the general answer to that question. And it's not easy, and it takes a long time, and it's fraught with bad turns and things you try and don't work out and things like that.
Okay. So that's a good explanation of how you look at what biological aspects are important and which ones can be ignored. I guess there's also a question of, if you're going to build a brain out of different stuff, could you do it? And what would you have to reproduce, and what could you do completely differently?
Yeah, I think that's, as a computer scientist, the actual physical substrate is not that important to me. What's important to me is the algorithm, and you can then re-implement the algorithm in anything that's Turing compatible. So it's really gets down to understanding the algorithms and the details, and then you don't have to implement it with ions and neurotransmitters and biochemical stuff. We can implement it just fine on computers.
Yeah.
The key is, go ahead.
Yeah, I agree with that. I interpret the question slightly differently. It's like, well, one way you said, what part of the biology we have to model, right? The other part is like, hey, are we going to be doing this on silicon? Or is it going to be something else? And are we going to use the same processes we use to design silicon chips today? Or are we going to use different processes? That's a really hard question to answer. If you look at the history of computers, of course, they started out with, vacuum tubes, and then they went to individual transistors, and they went to some sort of integration. Now we're billions of, transistors on a chip. What's going to happen here? I don't know, but, maybe we'll find some, it's not going to be like quantum computing or something like that, but there might be new substrates of physical substrates to implement this stuff. I mentioned briefly this company, Neuromorphic. What's the proper name of it? I can't remember. Sorry.
Yeah, Rain Neuromorphics.
Neuromorphic. And they have I don't know if they're going to be successful, but they have a really interesting new approach to how to build silicon chips that do this stuff. It's like, so it's just fun to look at that, and maybe they're right, maybe they're not. I don't know. But I think we'll see incredible innovation over the coming decades, where I know that I can't anticipate what's going to happen. I'm not smart enough to do that. I don't know if anyone can.
Great. That sounds like an exciting time. Well, looks like we're at the top of the hour. Maybe we have time for one more question.
Let's see here. I'm looking at here.
So if the representations are distributed, where do the votes in the voting system get tallied? That's a pretty specific question. So, kind of one surprising thing that came out of our modeling is that, if neurons are representing hypotheses using these sparse vectors that Jeff mentioned, where do you actually accumulate the evidence? And well, it can't be in some homunculus, can't be some external system. It has to happen within neurons itself. And it turns out, we think it's actually happening via the dendrites. So it's the dendrites that are getting context and accumulating that context and responding. So think about each neuron getting a bunch of contextual signals. The votes for different hypotheses are actually the different context signals coming in to these specific sets of neurons. And the more votes you get, the more likely the neuron is going to fire first. And by firing first and really strongly, it's going to inhibit the other one. So it all has to happen in this local, massively distributed way. And each neuron is doing something really simple. But when you step back and look at the overall function that's being computed, it's actually doing some sort of voting and accumulating hypotheses. But at the end of the day, it all has to happen with very simplistic rules within individual neurons. There's nowhere else.
You hinted at something here, Subutai, which is probably worth mentioning. As much of our theory, we test by building models. And the models can have varying levels of biological detail, but they do include the dendritic processing and the kind of connectivity we see. And so, it's useful. We find out things by modeling. We find out, does it really work? We know it's going to work probably, but how does it work? How fast is it? How quickly does it settle? What are the capacities? It's very difficult sometimes to determine the capacity of these systems. So we've modeled the voting system. And it worked really well. It was really simple in the end. I mean, we had a couple of tweaks to get it there, but it's not like a complex system. And I think that's one of the most coolest thing about this theory is that's what we perceive. That's the thing that we can remember. We don't remember. We can only perceive the output of all this voting. And so most of what's going on in the brain, you're not consciously aware of it. The voting is the only thing that goes long distances in the brain, right? Almost all the local computation in the columns, how could you talk about it? It's not connected to anything else, right? But the voting neurons do go long distance, and you can remember those states. So that's kind of a cool thing about the whole thing. All right.
Okay. All right. Thank you so much, Jeff and Subutai. It's been great talking with you. Any final thoughts before we close the session?
I have a couple final thoughts I wouldn't mind sharing. I don't think true AI is 100 years away. I think it's shorter than that, much shorter than that. We're talking 1 or 2 decades. And there's one thing we didn't bring up today, which a lot of people are worried about, is the threat of AI, the existential threat of AI. I'm unabashed in saying that I'm not worried about that so much, and I'm not worried about the existential threat of AI because we understand how these systems work and that they're not going to develop their own sort of goals. They're not going to the issues that are there. But some people misunderstand that and think that we're not worried about the risk of AI in general, and we are. And we think AI is an extremely powerful technology, and we have to be very, very careful how it's used and how it would be abused. But I think people who are worried about the existential risk, like AI is going to wake up one day and take over the world and not listen to us, I don't think that's going to happen at all. And I make that argument in detail in my book. So if you want to know about that, you can read about that. But I think we all, Google, us, everybody, has to really take these issues seriously when you create a powerful technology. It's going to revolutionize the world. It's going to make life so much better for so many people. It's going to advance our knowledge incredibly amount. But we'll have to be careful how it's used too. So I'll leave it at that. I think it's going to be exciting next 20 years. Just super exciting.
Okay. Well, we had an exciting time today, and we're looking forward to an exciting next 20 years. And,
yeah, thank you. That's great.
Thank you so
Thanks,
much,
Peter.
Thanks, Peter.
Right. Bye for now.
Bye.